Before we actually get into dealing with annotations, there's one other thing I want to talk about, and I mentioned this earlier, which is we added an additional package called data pasta, and I had mentioned this in the first part of the lecture that data pasta is a R package that lets you actually deal with pasting, copying and pasting data directly into your R environment. And I just think this is a really handy thing to know how to do. So I want to bring this up as yet another way to pull data in and before we move on and leave this idea behind. So I guess the first thing to point out is that data pasta is an R package, but it falls in this unique category of R packages called add-ins. And so add-ins are something that's unique to RStudio. You can find them at the top of the RStudio interface, and they really sort of extend the functionality of RStudio. That's the best way to describe it. And they give you an interactive way to work in R. So once you've installed data pasta and you've loaded it, what you're going to find in the add-ins menu, among some other sort of add-ins that I have that you may or may not have, and I wouldn't worry about, is at the bottom you'll see the data pasta functions, and you can see that they effectively give you a number of ways to paste data directly into R. So I thought I'd demonstrate this, and there's a couple ways I think are easiest to do that. The first is just directly from a spreadsheet or a text file. And so I have a large text file open of gene expression data actually that has a header, and it has two columns that are identical. They all have gene symbols in them, again identical, and a bunch of expression data. And so in Sublime, remember, and this is a good opportunity to just remind you, Sublime can recognize different kinds of structured text. So I can go down to the bottom right of Sublime. I can change this from plain text up to advanced CSV, because remember, I went in and got that advanced CSV plugin that we talked about in a previous lecture. When I click on this, the structure of the file is recognized in a different way. Now it sees the first two columns as text and the remainder of the columns as numeric data. I can now edit this a bit more, and there's a couple things I want to do here. The first is I want to click on the View menu and remove the word wrap default function. I don't want the rows to wrap, and this gets into something we're going to do next. So I'm going to deselect that, and then what I'm going to do is put my cursor anywhere around these gene symbols, and I'm going to pick an area where there's gene symbols of different length. So here ABI1, but then above it is a 5-character gene symbol, and then above that is a 7-character gene symbol. I'm going to put my cursor down here on ABL1, and I'm going to push Control Shift, and I think if this were a PC, I would hold Control Alt. And while holding on my Mac Control Shift, or on a Windows machine Control Alt, I'm going to key up. I can do what Sublime does really well, which is add multiple cursors to multiple rows. Now, still holding down Control Shift on my Mac or Control Alt on a PC, if I now move with my arrow button to the right, so keying over to the right, I can see my cursors jump, and they jump to a break, basically a border between text and numbers. If I key over again, now I'm close to the end of all of the gene symbols for that row. I key over again, and now I'm at the end of this long gene symbol, but I've overshot the shorter gene symbols. So I'm going to key back to the left and then back over to the right. Now I basically adjusted the position of the cursor so that it's at the end of all of the gene symbols, regardless of their length, and they're selected. I can see they're shaded because I was holding down that Control Shift. Now I'm just going to release all the keys on my keyboard, and I'm just going to copy. Apple C on a Mac, Control C on a PC. So I've copied these gene symbols, and you can see how this could work for any length of selections in a column. And this could happen in Excel too, right? I could just select a whole column from Excel. It doesn't matter. I'm just showing this in Sublime so that you get a better handle on how Sublime can handle and deal with text files. So I've copied that, and what I'm going to do is head over to my RStudio session, and I'm just going to, right below where I read in my study design file, I'm just going to type test and my assignment operator, and that's it. And now I'm going to go up to the add-ins. I'm going to click the add-ins and select paste as vector. When I do that, it recognizes that I have something copied to the clipboard on my computer, and it's going to paste it in as a vector. All right. Now that is extremely handy. If you don't appreciate why that's handy, you will as this course moves on. This idea of, rather than typing numerous different gene symbols, right, I can just copy from a column structure in Excel or in a text file, and I can paste in as a character vector. Now, when I execute this line of code, I have an object called test that if I run, it's all of the gene symbols I selected. This is going to become really useful in the future when we have to sort of, reach into a large gene expression data set and grab a bunch of gene symbols that we want and just plot those, or just look at a heat map of those genes. It becomes really easy to do this. Okay. What about other kinds of data structures? Well, really the data pasta package will let you copy and paste and create data objects in R from virtually anything. So as an example, if I go back to my web browser and I go over to just a table in a website, and this is just one I just found on Google, I don't care the content of the table so much. I've just highlighted it and I've copied Apple C on a Mac, Control C on a PC. And I'm going to go back to RStudio, and I'm going to say test2, just so I don't overwrite it. My assignment operator. And I'm going to go back to the add-ins menu, data pasta. This time, though, I don't want this as a vector, right? It's not a vector, it's a table. So I'm going to paste it in as a data frame. All right, I know it's a data frame, it's got lots of text in it. And so I'm going to choose that, and it immediately structures it exactly as I need. And all I have to do now is hit enter and scroll back up and highlight test2. I can see I created test2, 6 observations of 3 variables. If I just execute that test2 bit of highlighted text, then I can see I got the table from the website in exactly as it was rendered on the website, but now it is a data object in R. It's a data frame, test2. And just like my targets file, it's ready to be used in the R environment. All right. So you could do this with any data structure. You could do it with Excel spreadsheets, with columns, with really anything. All right. So I'm going to delete all that test information. And so we now have our study design read into R. We have file paths. We know those file paths are valid. And we have a sense for how to read data into R in a couple different ways. So I think that's a really good start. Now we want to sort of switch topics a bit, right? We're entering a different code chunk here, different theme. In this case, this is something that's not general R. This is really topical to dealing with gene expression data, and that's the concept of annotations. Annotations, as I mentioned in the first video, represent a real stumbling block for or hurdle for many gene expression studies. And that's because it's challenging sometimes to know where to go get this annotation information. It's not immediately apparent if you're new to this kind of analysis why you need annotations and what they are. So we're going to go over that now, and I'm going to tell you about 2 different strategies for accessing annotations. The first strategy, if you're lucky, is that you work with an organism that has what's called an organism-specific annotation package or database package. Let's just say that's only going to apply to you if you work in human mouse, or rat. Now, if you're curious whether there's an organism-specific database package for your organism, you can go to Bioconductor. Bioconductor has an entire part of their website devoted to annotations. It's down here. You can see the annotation hyperlink. When you click on that, you're going to be taken to a site that has a lot of different kinds of annotation packages. These are all Bioconductor R packages. They break it up by different kinds of annotation packages. The organism-specific annotation packages is really what you want. And they really run the gamut of different kinds of organisms and different kinds of annotations. All right. We're going to go back to RStudio now. And for the purposes of the data set we're working with in class, it's human data. So I need a human database annotation package. And luckily, our Bioconductor provides not only an option for that, but it provides even several options. And those options really are different depending on the release or the version of the human reference data. So I choose the most current version, and I use the transcripts function. That transcripts function comes from the EnsembleDB package, and it lets me go into this database R package and get out information at the transcript level. Now, I could just provide that single argument to the transcripts function, and it would return an object here. I'm going to put a handle on that object called tx so that I can call on it later. But I want to add an additional argument, and that is I want to make sure that no matter what transcripts function, no matter what it pulls out of this database package, that it at least gets me 2 columns and 2 specific columns. Now, I've dictated exactly what those 2 columns are, and I just know that these are the 2 columns I need. There's no way for you to, sort of just intuitively guess that. You would have to look at the EnsembleDB Homo sapiens v86 database package and see which columns pertain to you. For the purposes of most of the work you would do in this class and even beyond, these 2 column labels are the ones you would want. Okay, so if I run this line of code, it's going to create a tx object, and it's digging through this database package now. It's a large package, so it takes just a second. And now I see I have a large object. It's not a data frame, it's not a data matrix, it's not a vector. It's a special object that is called a G-ranges or genomic ranges object. Now, we don't need to dig into exactly what kind of structure a G-ranges object has, but I'm going to immediately take that object and I'm going to turn it into a data frame. Now, I can do that because the tidyverse set of packages has a function called asTibble. You can think of it as table. Tibble is a funny word made up by the folks who created the tidyverse ecosystem, in particular Hadley Wickham, a real star of R, who now is the chief scientific officer for RStudio. He created this notion of a tidy table, so Tibble. And we're going to get in the next lecture into more detail about what it means to have tidy data. Let's just kind of gloss over that for now. But suffice it to say, I can take this object tx, I can sort of coerce it to be a tibble, and overwrite the previous state of that tx object. So that means that the object tx as I have it now will be altered. It'll be overwritten. All right, let's run that line of code. And now I can see that this is no longer a G-ranges object. TX has 216,741 observations of 7 variables. It is now a data frame. All right, if we click on TX, just as I showed you earlier, clicking on any sort of data frame or data matrix object, anything under this data header, will open it in the viewer. It'll execute a line of code that says view parentheses tx. There it is, view parentheses tx. And sure enough, I can now appreciate the structure of what it is I retrieved from this ensemble database package. I have a start and end position to sequences. I have a length of the sequence, whether it's on the plus or minus strand, and a transcript identifier and a gene name. This is key. This is what I was after. I now have transcript identifiers mapped to gene symbols. Why is that important? Well, in order to appreciate that, we kind of have to come back to our initial data. I'm going to come to that now, which, remember, Callisto outputs this abundance.tsv file. And that abundance.tsv file has transcript level information. There it is. Ensemble transcript IDs, their length, their effective lengths, which we discussed in the previous lecture, and then how much transcripts per million, also discussed in the previous lecture. So this is a problem. We really have trouble attaching meaning to these kinds of long ensemble transcript identifiers. We'd like to know what gene this transcript originates from. And in order to do that, that is a job for annotation packages. That is a job that requires taking all these transcripts, of which there are 187,000 of them, and mapping them to gene symbols. All right. So back to RStudio, that's what we've done. We have some extra information here, but we importantly, we have the transcript identifier and we have the gene name. Now, that's the first sort of key part of this. I guess the other thing to the other takeaway message from annotations are that you can get anything. Any gene or transcript level information can be pulled from a database package or from, as I'll show you in a minute, from a separate resource called Biomart. And you could get, all kinds of different identifiers, start and stop positions, length of the gene, how many introns or exons it has. Those are all annotations, information about genes, information about transcripts. All right, I'm going to go back to my script here. All right, so I have this TX object created. I now have a sense for what's actually in this data frame. And now I have to do some gymnastics with the data, some wrangling. This is a common thing to have to do. It's not so intuitive why or what to do, so I'm just going to tell you why and what. The why and what have to do with what I'm trying to do downstream in this script. I want to read my Callisto data in, and I know that in order to do that, I would like the option to be able to collapse or map my transcript level gene expression data to gene level expression data. And if I'm going to do that, I need to have this one-to-one mapping of transcript IDs to gene symbols. Okay, so Callisto, like many programs, I should rephrase this. The R package that's going to allow me to read in my Callisto data has, some strict criteria for what it's looking for. And one of those criteria is that it looks for the transcript IDs and the gene IDs to be in columns that have very specific names, right? It can't just be gene underscore symbol or gene dot symbol, right? You could imagine there's a number of different column names you could use. So they enforce certain column names. So the first thing we're going to do is abide by those standards. We're going to take that data frame TX and we're going to take the column currently named TXID. So let's just look at TX again. TXID, this column that has the transcript identifier, and we're going to rename it to target ID because target ID is what the package that reads in our Callisto data will be looking for. It won't recognize TXID. All right. It also will look for a column called gene underscore name. We're in luck. This is called gene underscore name, so we're good. All right. How do I do that? How do I take this data frame where I understand its structure and just do only one small thing, which is change the header for this column? Well, we do that using a package called dplyr, and a function from that package called rename. As the function name suggests, rename lets you dip into a spreadsheet, a data frame in this case, choose a column and rename it to this column. And the renaming, the name you want to use always is listed first. So a couple things here. dplyr is a really useful package we'll use a lot more. In the next lecture, we're going to get into more of the details about dplyr. I want to just sort of gloss over this for now because we're only using 2 functions here from it. We'll talk more about the different dplyr so-called verbs or these functions. And I want to also highlight that this is one situation where I didn't just list the function name, I listed the package followed by a double colon and then the function name. Why now? Why did I do that? Well, partly because, and mostly because, the function names are really generic. Rename, select. You know, in the ecosystem of other packages I have loaded, which if I scroll down through here, you can see check marks next to a lot of different packages. It's possible that one of those other packages has a rename function or has a select function, and there would be a conflict. And we already talked about these conflicts in the first part of the lecture, that tidyverse packages sort of already try to anticipate some of these conflicts and deal with them. But one way to just deal with it right away up front is to explicitly state the package name followed by 2 colons followed by the function. That will require that this function that's being used comes from this package. That's it. You could in fact do this for every one of your functions. You could always say the package name and 2 colons and the function name. But I only do it when there's ambiguity in the name of the function. All right, so we're going to rename in the tx data frame. We want to apply this name to this column. All right, so I'm going to run that and we'll peek again at tx. And when this opens up, we'll see now we have target ID instead of tx underscore ID. All right, one other sort of dplyr function we're going to use is select. And select lets us essentially, as the name suggests, select specific columns from our spreadsheet. We don't care about, in this case, we don't care about start position, end position, width, strand. We really just want this one-to-one mapping of transcript IDs to gene symbols. This is an example of, in the world of annotations, there's a lot of stuff we don't care about. And for the purposes of what we're trying to accomplish, we just need this. So I'm going to use this select function. Again, the first argument is the name of the data frame. The second argument in this case is the column I want, and the third argument is another column I want, and this could continue. We'll talk more and you'll learn more about how to use rename and select from the dplyr package. Again, I will save a lot of that sort of unpacking of dplyr for the next lecture. All right, I'm going to run this, and again, because I've used my assignment operator to apply this result to an object called tx, then it means that tx is now overwritten with this new object I created, right? This new result. And that is a table with just 2 columns, transcripts and gene symbols. Okay, so I'm close, very close to being ready. I'm actually ready to read all of my Callisto data into R, and at the same time, give that function that will do that reading in, give it this mapping. And it will allow me to choose. Do I want all my data sort of collated together as a single spreadsheet at the transcript level? Or do I want it all collapsed, if you will, to the gene level? And what I mean by that is, look at this example. Here, rows 5, 6, and 7, 3 different transcripts, 3 unique transcript IDs, all mapping to the same gene. Do I want this in my spreadsheet represented as 3 rows or 1? And that's really the key decision we have to make. It's one that you get to have your cake and eat it too, which is you can make both spreadsheets. You can make one that has transcript level data, and you can make one that has gene level data. There's a paper, the paper that describes the package we'll use to do this. it makes the case that it is best to align your data at the transcript level, but then use that transcript level information to summarize to gene level. It gives you sort of multiple measurements of the same gene and gives you the most robust estimate of gene expression. So what I typically do is I do collapse to gene symbol, partly because of that added value of using multiple transcripts to assess the expression of a gene, but also because I find it hard to relate a lot of times to these individual transcript identifiers, and much easier to have conversations, have data displays, have results that are annotated with gene symbols. People, relate to gene symbols. Okay, but we are ready now to actually do the reading in. We have our mapping, one-to-one mapping, and we know where our Callisto outputs sit. But I want to take a small departure here, but it's a really important one. And that is, there's another use case, if you will, for annotations, which is you don't have mouse or human or rat or one of these really common model organisms. You have dog, horse, sheep, Colorado spotted newt. Where do you get your annotations? And that's why I mentioned this is a real hurdle or obstacle for many people, is finding these annotations. So if you have a different organism you're dealing with, or perhaps the annotations you want are not so simple, it's not just transcript ID and gene symbol or position or start or end, it's something more detailed, that might not be present in the Ensemble DB, version 86 package for Homo sapiens. So in that case, I wanted to let you know there is a lot of other options for accessing annotations, and one of the most extensive is through a package called Biomart. And Biomart, as the name is supposed to imply, allows users to connect to a database of a mart of many different annotations. You can, the analogy would be you walking through a Walmart, and you have a number of different annotations you could choose from, but you can go specifically to the aisle you want and the section of that aisle you want and just get the things you want, right? So it really is this extensive annotation warehouse. So I've described a little bit more about Biomart here. I thought I'd just demonstrate how this works. And to do that, I'm going to pretend that I have a need for canine annotation data. I've done RNA-seq on dog tissues. I've aligned to the reference dog transcriptome from Ensemble's FTP site, which I actually showed you in that lecture, and produced transcript level abundance data for every transcript annotated in the dog transcriptome. Now I need to map those transcript IDs from dog to gene IDs, gene symbols from dog. How do I do that? Well, I'm going to walk through how to do this, and this gets into, again, a little bit more teaching, and we'll strip this stuff away in that essentials code chunk at the bottom. But the first thing you can do is just take a look at the marts, if you will. Again, that's the notion of being able to go in and get a bunch of stuff. List the marts that are available to you. So I'm going to run this function list marts with no arguments specified. When I do that, I have 4 marts I can choose from. Ensemble mart ensemble, which is Ensemble genes version 99. There's a mouse strains ensemble. There's some, I think, a SNP database, and then functional genetic sort of gene regulation stuff. I won't pretend to know much of anything about these bottom 3 marts. I never shop in those stores, so to speak. I'm always operating in this top mart, which is Ensemble genes. So that's what's available. Now you have to, you apply the useMart function, and you tell it what biomart you want, and you need to be exact, case sensitive, everything. So as you can probably guess, I'm going after this one. So I say useMart, this is the one I want, and put that mart in this object, and I'll call this object myMart. All right, I have this object. It's of the formal class Mart. We, again, don't need to kind of unpack what that might mean, but we're not going to really dwell on that because we have more we're going to do here. The first thing that we're going to do is take a look at all the available data sets within that selected Mart, and it's extensive. So I'm going to use the list datasets function from the BioMart package and apply that to this myMart object. And I'm going to store the result as something I just call available.datasets. Again, when we, just to kind of reiterate, when we make files, objects, folders, anything in when we're working, in command line tools and programming languages, we don't use spaces. That applies here too in R when we're making objects. So I'm going to run this line, and I now have an object called available datasets, and I can tell already from the sort of look of this that it's a data frame. 202 rows or observations of 3 variables or columns. If I click on this, I can see that it is an extensive list of organisms, the description of those organisms, and the version. And it really is extensive. I mean, we have, American bison, wild yak, even the Siamese fighting fish, right? Extensive. And I can search this for Canis, C. familiaris, there it is. You could also search it for dog, right? That'll turn it up as well. So this is what I'm looking for, right? It happened to be row 26. I'm taking advantage of this ability to search in the data browser here. C. familiaris gene ensemble dog genes called CanFam, Canis familiaris, version 3.1. Great. So I know what I want. Now I'm going to go ahead and get it. So I use the useMart function again, but I get more specific this time. I still say the Mart, but now I know the data set. So I'm supplying an additional argument called dataset. And I'm, again, very verbatim, pulling from that exact, row name that I saw in that spreadsheet when I was just looking at it. And I'm going to put that into an object called dog and anno, dog annotations. Okay. So that's created. It is a large Mart. It's almost a megabyte. I'm not going to dig into that right now, but I'm immediately going to ask, using the list filters function, what are the sort of ways that I can, because right now, what I just pulled out with dog anno is all of the gene level annotations for the canine genome. It's extensive. So before I go and look at that, I want to know what filters I can use to kind of parse that. So I'm going to list filters dog anno, and I'm going to store that in an object called dog filters. And now I'm going to highlight dog filters and run it. And I can just also click on it, remember, and it'll open in a little bit easier to read format. And I can see that this is 336 rows long. Each of these is basically a spreadsheet, right? Each row corresponds to a level of information I could get out about every gene or transcript in the canine genome. I could find out, all the KEGG enzymes. I could ask for UniProt IDs. The list goes on and on. I could get orthologs for certain species, orthologs for all the gorilla genes. So you can see why I need to look at these filters, because there's a lot of stuff here I just don't care about. I don't care about orthologs between dogs and Tasmanian devils. So all right, I can tell you when you look through this, there's really, again, 2 things I want. I want the transcript ID version, and I want the external gene name. Now, how did I know they were exactly called that? It doesn't take long. I mean, if you actually search this for transcript, you're going to come down pretty quickly with some ideas of probably what you're looking for, and just peeking at them, or capturing those objects and looking at them, lets you know pretty quickly what you're looking for. So just as I had done with the human ensemble organism specific database package, here I'm just using BioMart, but the goal is the same: get the transcript ID to gene mappings. All right, so I execute that line of code, and now I'm going to convert that into, again, a tibble. Right now, this tx.dog is here, and it's a data frame. And we understand data frames. They're a spreadsheet that contains a mix of different types of data. Could be text, could be numeric data. But we understand that a tibble is a kind of tidier version of these data frames. So for example, when I just asked to look at tx dog before I converted it into a tibble, it prints off 500 rows. And then it says I reached the max and I've omitted 60,494 rows. It also, if there were more than 3 columns or 2 columns here, there's row numbers and 2 columns. If there were 8 columns, it would do this annoying wrapping of the columns, and it really is really cumbersome to look at. Turning it into a tibble will clean that up. It's a tidy table, right? So if I convert that into a tibble and now I look at tx dog, which still is a data frame, but it's been tidied up, it looks a lot different. Now it only prints the top 6 lines. It tells me the dimensions of the data frame right at the top and tells me it's a tibble. It tells me how many more rows I have, and it tells me what kind of data, character, vector in this case, character, are in each column. So it's more compact and easier to parse visually by people. All right. Just as we did when we dealt with the human database package, we want to use dplyr's rename to make sure that the names of these 2 columns are compatible with what we're going to do downstream, with the package, the program that we'll use to read in our Callisto data. If it tries to take our Callisto data and use these columns to map to gene symbols, it's not going to like the names of these headers. So we have to be cognizant of that and use this dplyr rename to make sure that the first column is called target ID and the gene symbols are gene underscore name. Last time it was already called that, so we were in luck. This time it's called external gene name, so we're going to rename it. All right, so we'll run this again. We will take a look at tx dog again, and sure enough, we now have our successfully renamed columns, and we're good. Now, I'm going to open this in the data browser because I want to highlight that, this is what you get sometimes with non-model organisms, is we have transcript identifiers and we have gene symbols, but you'll see a lot of transcripts are not annotated or not mapped to a gene symbol. And that's because there's a lot more issues with annotations in non-model organism genomes than there are in human mouse. We can see here's 6 different transcripts that all map to a collagen, I think a collagen gene, but you can easily find stretches where there's transcripts that don't have clear one-to-one annotations, and we just don't know what those are. So again, this comes back to this issue of you'll want to think carefully about what you're looking at if you're looking at transcript level data and how that changes if you're looking at gene level data. In the dog or in any other organism that's not well annotated, we might lose a lot when we collapse to gene symbol. All of these transcripts that have no gene symbol annotation will all collapse to one thing, unlabeled, one unlabeled row. And so that's important to understand, that there's this trade-off, right? All right, now you understand how to use an organism-specific database package if you're working with mouse or human. But if you're working with something else, or you need a broader range of sort of annotation data to tap into, you also understand in this other code chunk that I've labeled optional how to get annotations from something called Biomart. Great. So now we are ready to actually get down to the business of reading our data into R. To do that, we're going to use the tx for transcript import package. It is a package that allows you to read transcript level data in from a variety of different aligners. Callisto is one of them, but so is Salmon and other pseudo alignment or alignment free algorithms. And we have a few arguments, right, that we have to provide to tx import. And so there's a couple things to point out here. The first is, just as I did when we ran Callisto at the command line in the terminal, here with tx import, I've got enough arguments here that I don't feel comfortable stringing it along as one line. So after every comma, I've hit return, and I've vertically stacked the code so that it's easier for me to go in and sort of, well, to visually just parse it and change things. All right. Now, RStudio is smart enough that if I just am typing code and I hit enter, it understands how to align these. It understands that this is a continuation of the line above, so it lines them up vertically. So I didn't have to tab to do that. It just does it. The other thing, the other advantage this offers, and this is really key, is that if there's a function that I want to toggle on, not a function, if there's an argument that I want to toggle on or off, I can do that now just by adding a pound sign in front of it. And that doesn't comment out the next line, right? Comment hash marks or pound signs only operate on the line they're on. So that's a big difference from if I had this whole thing on one line and I put a comment, here, it's going to comment out these two arguments. So having this sort of stack like this is just another sort of, I don't know, convenient way to work with your R scripts. All right, so let's talk about these arguments. TX import is going to, the first argument is that it needs to know the paths. Where can I find these Callisto outputs to read in? So we created this path up above using the file.path function, and we know that that's a character vector of length 10. Each element in that character vector is basically stuff pasted together from our targets study design file and then the word abundance.tsv. We also have an argument of what type of alignment data we're reading in, and we're going to tell it that that's Callisto. Then, importantly, it's asking if we want, if we have a mapping of transcripts to genes. And indeed, that's what we just spent the majority of this time above doing with our annotation lesson. We were taking our transcript information and pulling genes from the annotation database to make these one-to-one mappings. And indeed, we have this object called TX, and we know that that's formatted right. I'm telling you that this is what TX import wants. It wants to see target ID and gene name. And so we have that one-to-one mapping. Now, it also wants to know, great, so you provided me with this TX mapping of transcripts to genes. Now, what do you want out? Do you want transcript level data or do you want gene level data? And the argument that dictates that is called TX out. And if TX out is set to true, it will output transcripts out. If that's set to false, it will output gene level data. The next argument is how we want to sort of take the abundance data we have in transcripts per million. Remember that file. I don't know if I still have it open. I do not. Let's just open it. That file has our transcript identifiers, and it has length, effective length, counts, and TPM. So what TX import is asking us here is how do we want to calculate counts from abundance? And we're going to use the length scaled TPM. And then a nice new addition to the TX import function, and one we used to have to do a really annoying workaround for, is do we want it to ignore the transcript version? Long story short, all of the reference transcriptome we used that we used for our alignment that led to this data has these annoying transcript versions appended on the end, a decimal .1 or .2 or .3, and if you notice, our one-to-one mapping file TX doesn't have those. It's missing the versions. And in the past, that used to throw an error. Basically, it would say, I don't see this transcript because in our data, it ended in a .1. So now they added a function to ignore those transcript versions in our Callisto abundance.tsv file. All right, so I'm going to go ahead and run this. Again, even though this is, stacked on different lines, hitting run or Apple enter or whatever that your keyboard shortcut is will execute the whole piece of code because it is one contiguous piece of code. And so that's it. It says, hey, listen, note, you might want to think about importing instead of abundance.tsv, set your paths to point to the abundance.h5. It's faster. We've ignored these abundance.h5 files because Callisto is going through a change right now where they're moving away from this H5 file format to something else. We'll see what happens. But that file used to store the abundance data with bootstraps. So we're just kind of ignoring bootstraps, ignoring this whole concept. You understand what they are from previous lectures, but we're not going to handle them or deal with them. Okay, so that's great. It took all that data and it summarized the abundance, summarized the counts, and summarized the length, and it created this TXI gene object, which is a large list. Now, we'll talk about lists more in a future lecture. We don't have time now, but a list can be a collection of any different kinds of R objects. It can be multiple data frames, a data frame, and character vectors. But that list in this case has 4 elements, and we'll talk about what those elements are in just a second. But you'll see that there were about 9 or 10,000 transcripts that were in our data, but were missing from the annotations, meaning they weren't in that TX to gene mapping. Is that something to be concerned about? Well, this is an issue with annotations. It's never exhaustive. It never includes everything. This is, less than 5% of our data. But we can keep an eye on this. I just want to make you aware of it. Okay, it's done. I have this included at the end just to lighten things up a little bit. You can use the beep function from the beeper package at the top. And that's just, again, just for fun. You can put that at the end of things you're going to run. And if we had highlighted that code, at the same time and run the whole thing, we would get this. And this is going to finish all of the reading in of the 10 files here. And again, it gave us that little note. And as it finishes up,
we're ready, Master. I'm not ready.
You can choose different video game sounds. How great is that? Here, let's try number 2. And I'll just run this single line of code. I don't know how old everybody is in the class, but hopefully you recognize that sound. Let's try number 3. Brings back memories for me. Okay, so now we're done. We've read in our data and we have this TXI gene object. We can kind of unfold that and see some of the structure. It has abundance, it has counts, it has length. So before we close, just to show you, if we're ever unsure about what kind of object we have, if we can't infer it from looking over here, which is actually probably the easiest way, we can always run the class function on an object. It tells us it's a list. We already knew it was a list, but these things are all retrievable at the command line as well. If we want to know what's present in that list, then we can ask for the names. Names will let us access all the elements in a list. And we can see that it has 4, right? Large list of 4 elements. And those elements are abundance, counts, length, and counts from abundance. All right, so that's it for now. I also just included this print step 1. You can see we tell it using the print function. We're done with step 1. All right, that's it. In the next lecture, we're going to pick up and actually dig into what's in this object we read out. I'll remind you that there's, and I'd encourage you all to play around, you can toggle this to true, and your data will have not gene level data, but transcript level data. All right. And then lastly, as I mentioned before, stripping away all the kind of didactic stuff and the goofy beeper leaves us with a minimal amount of code that we actually need to do this, right? Reading in the packages we need, reading in our study design file, setting our file paths, pulling transcript level data from our human database annotation package, converting it into a tibble, tweaking that tibble a little bit to make sure our column names are all right, and then running the import. All right, that's it. That concludes today. I just want to wrap up with a few key notes so that we're all on the same page. So, our code in packages. Organize your code in chunks. It gives you the advantage of being able to have this table of contents and always know where you are. Create new chunks by ending a comment line with 4 dashes. Setting repositories lets you have a much broader reach for installing R packages. Unfortunately, you're going to have to do this each time you sort of open the RStudio session. And use that double colon if you ever want to enforce package function relationships. Getting data into R. RStudio add-ins let you execute R code interactively, and we showed you the data pasta add-in. That's just one of them. We'll play with others along through the course, but you should look into these add-ins as well. They just give an extra functionality to RStudio that I think is really useful. You can use the tidyverse read dlim from the reader package to get data from a file on your computer into R, but you can use data pasta to get data from your clipboard, copy and paste into R in the form of tables, vectors, whatever. Understand the difference between a data frame and a data matrix. Data frames have a mix of different data types, text or character vectors or characters, and numeric data. A matrix has numeric data only. It can still have row names, but it's the body of the spreadsheet is numeric data. You can use the view function, capital V, to open any data frame or data matrix in the table viewer. You can also just click on it in the environment, in the global environment browser, and it'll open, essentially running this code for you. And then lastly, you have a bunch of data sets available to you. You can use the data function to list those data sets. And if you add the name of a data set in these parentheses, it'll load that data set and display it for you. All right, and lastly, you can get help directly in RStudio. Use the question function followed by the name of a function, or equivalently use the help function and list the name of the function inside the parentheses that you're looking to retrieve help documentation on, and that'll retrieve the help docs, open them in the help tab for any function. Just a point though, that package has to be loaded for you to be able to access its function via these options. Finally, R code can be run directly from help docs. So once you've accessed a help doc, if there's something you want to try or understand how it works, just highlight that code in the help doc and hit run. And that's it.